Welcome. We are about to dive into this hidden world, this invisible force that connects a tiny little quiver to some of the most powerful technologies on Earth. Yeah, we're talking about the physics of vibration and sound, and trust me, it is a seriously fascinating ride.
So, let me ask you a question. What on earth does a guitar have in common with a microwave oven or a deep-sea submarine? I know, sounds like the beginning of a bad joke, right? But the answer is this incredible, powerful idea, the physics of vibration. Stick with me, and you are going to see exactly how these three completely different things are all deeply, deeply connected.
All right, to get our heads around all that, we need to start small. And I mean really small. We've got to look at the most basic, the most fundamental movement that is the foundation for everything else we're about to talk about.
So it all starts with something called simple harmonic motion, or SHM for short. Just think of it as the purest, most perfect, most predictable back-and-forth movement you can imagine. This simple, rhythmic dance is literally the atom, the building block for all the waves and all the sounds that shape our entire world.
Now here's where it gets really cool. The energy is always changing. The perfect way to picture this is a kid on a swing. You know that moment at the very top of the swing when they hang in the air for just a split second? That's all potential energy. It's stored up, ready to go. Then, as they swing down, that potential energy transforms into kinetic energy, the energy of motion, which is at its max right at the bottom. And this constant trade-off, this swap between potential and kinetic, it's happening inside every single vibration all the time.
So what happens when you get a whole bunch of these particles all doing this little dance together? Well, you get a wave. Think about it like a line of dominoes. The first domino doesn't slide all the way to the end, right? No, it just tips over and passes its energy to the next one, and so on. That is exactly what a wave does. Each particle is just vibrating in place, doing its own little simple harmonic motion, but together they pass that energy right down the line.
Okay, so we've got the basic dance down. Now let's see what happens when we start adding some outside forces into the mix. This, my friends, is where simple vibrations go from a gentle dance to something wild and incredibly powerful.
You know, vibrations really come in three main flavors. First up, you've got free vibrations. You give something one push, like you strike a tuning fork, and it just vibrates at its own unique natural rhythm until it fades out. Then there are forced vibrations. This is when an outside force just keeps pushing, like traffic constantly making a bridge shake. But the real magic happens with resonance. This is when that external push perfectly syncs up with the object's natural frequency. Go back to that swing. A parent giving perfectly timed pushes can send that swing soaring with just a little bit of effort. That is resonance.
And this brings us to an absolutely crucial point. The energy transfer is at its absolute maximum during resonance. It's the sweet spot. It's where a tiny, perfectly timed push can create a massive, almost unbelievable effect. Now, this power can be an amazing tool, but it can also be incredibly destructive. I mean, this is the very principle that famously caused the Tacoma Narrows Bridge to tear itself apart. So this isn't just some cool party trick, it's a fundamental force of physics that engineers have to take very, very seriously.
And you use this principle literally every day. When you tune a radio, you're adjusting a circuit to resonate with the frequency of a specific station. And your microwave oven? It's doing the exact same thing. It floods your food with microwaves that are perfectly tuned to the natural resonant frequency of water molecules. This makes those water molecules vibrate like crazy, which generates the heat that cooks your dinner from the inside out.
Okay, so we've got the basics of vibration down. Now let's zoom in and focus on the vibrations we can actually hear, and more importantly, how we can control them. Let's dive into the science of acoustics. You know, we tend to use the words echo and reverberation like they're the same thing, but in physics, they're actually quite different. An echo is a single, clear, distinct reflection. It's you shouting into a canyon and hearing your voice come right back at you. Reverberation, or reverb, is something else. It's what happens when there are so many reflections in a room that they all blur together into one continuous, fading sound.
So what's the difference? Well, it all comes down to this number, 0.1 seconds. See, our brains need at least 1/10 of a second between two sounds to tell them apart. If a reflected sound gets back to your ear faster than that, your brain just mushes it together with the original sound, and that's reverberation. If it takes longer than that, you hear a separate, distinct echo. Simple as that. In fact, architects and sound engineers have a very precise way to measure this echoiness. It's called reverberation time. Basically, it's just a measurement of how long it takes for a sound in a room to completely fade away. And as you can guess, getting this time just right is absolutely critical for designing everything from a world-class concert hall to a perfectly quiet recording studio.
So, how do you actually control it? Well, you don't need a PhD in physics to get the basics. The reverberation time in any room really just boils down to two simple things: its size, how big it is, and how much soft, sound-absorbing stuff you have inside it. Bigger rooms with hard surfaces mean a longer reverberation. It's really that straightforward.
And controlling it is all about practical things. This is exactly why movie theaters have those plush seats and carpets on the walls. It's why recording studios are covered in those foam acoustic panels. And here's a fun fact: even you, when you're sitting in a concert hall, are part of the acoustic design. Your body and your clothes absorb sound, helping to fine-tune the room's sound perfectly.
All right, for our last section, we're going to go beyond the limits of human hearing. We are stepping into a world where sound isn't just something you listen to, it's something you can use to see. Welcome to the amazing world of ultrasonics.
It's kind of humbling when you think about just how small our little sliver of hearing really is. Most of us can hear frequencies somewhere between 20 and 20,000 hertz. Anything lower than that is infrasound, anything higher is ultrasound. We are totally deaf to these massive ranges of sound, but that's exactly what makes them such powerful tools.
Now, here's the secret sauce. High-frequency waves have a really, really short wavelength. You can think of it like using a measuring tape with incredibly fine markings. This super short wavelength allows ultrasonic waves to bounce off tiny objects and create incredibly detailed, high-resolution pictures, something that the long, clumsy wavelengths of the sound we can actually hear could never, ever do.
The classic example, of course, is sonar. That stands for sound navigation and ranging, and the way it works is just beautiful in its simplicity. A sub sends out a ping, a short burst of ultrasound. That sound pulse travels through the water, it hits something, maybe another ship or the ocean floor, and it bounces back. By just measuring the time it takes for that echo to come back, the submarine can calculate the exact distance to that object. And once you get that core principle, send out a pulse, listen for the echo, you start seeing it absolutely everywhere. It's the very same tech behind a medical sonogram, creating those first incredible images of an unborn baby. It lets engineers find microscopic cracks deep inside a jet engine without having to take it apart. And it's what allows the parking sensors in your car to start beeping just before you back into a wall.
So just think about where we've been. We started with just a single, simple shake. From there, we built up to waves, we figured out how to sculpt the sound of a room, and we ended up using sound we can't even hear to map the bottom of the ocean. It all comes from that one simple vibration, which really just leaves one question, doesn't it? What's the next invisible world we're going to reveal with it?